Okay. Yeah. Okay. Silence, please. So, in the last class, we looked at a few formal features: soundness, completeness, and consistency. So, soundness is a formal system is said to be sound if all the derivable statements in that formal system are a subset of the statements in the corresponding universe. Okay. So whatever statements are derived, only true statements are derived. Some true statements may be not derived, but whatever are derived, they should be true. They cannot be a false statement which is derived. Then the system is said to be sound. And completeness is all the true statements in the corresponding universe are derivable within this formal system. Then the system is said to be complete. All right. And consistency, if both P and not P, they should not be derived in the system. Only then the system is said to be consistent. If both P and not P are derived in the system, then the system is inconsistent. It doesn't matter whether P is true or false. You can derive some false statements, you can derive some true statements, but you should not derive the opposite of any of these statements. Okay, so if there are contradictory statements within the system, then the system is said to be inconsistent. Okay, so these three things we discussed, and then the fourth thing I wrote here, you can note down. So fourth thing is decidability. So a formal system F is said to be decidable if there is a method by which, given the system's axiom set A and a statement S, this method can say whether S is derivable from A or not. So this is again a different formal feature. So what this is saying is, some statements may be derivable within the system, some statements may not be derivable within the system. Derivable means you have some axioms, you have some rules. From these axioms, you derive some conclusions. Like deduction we saw, you have premises, you have conclusion, and so on. So your axioms can be the premises, you can have a conclusion, and then that conclusion can be the new premise. You can have further conclusions and so on. Okay. So any statement, some statements may be derivable within this system using these axioms, some statements may not be derivable using these axioms. Can I come up with a general method which tells me, given any statement, whether that statement is derivable from this system or not? It may not tell me the actual steps. It at least just needs to tell me whether this statement is derivable from the system or not. Okay. So can I have a general method given the set of axioms? Again, I see you. If I listen any more word, I already looked at you. So can I come up with a general method where, given a set of axioms and some statement, this method tells me whether this statement is derivable from this set of axioms or not? If I can come up with such a method, then my system is said to be decidable. Whichever statement you give me, I will say, okay, this statement is derivable in my system, this statement is not derivable in my system. All right. So if it is not derivable, I need not spend any more resources in trying to derive it. Anyway, it is not derivable. It may be true or false, it does not matter, but it is not derivable in my system. Okay. If some statement is derivable, then maybe I'll spend resources in trying to derive it. Somehow I know it is derivable, I don't know how. Okay. Then maybe I'll try deriving it. All right. So this is again the different feature. This is fourth feature. Okay. Now, given all these different features, so why are we discussing all this? To come to the idea of Turing machine, because this course is about formal models of computation and the problems Turing stumbled upon the idea of a Turing machine. Okay, so I'm just coming to that in a while. So, but before that, there was another mathematician called David Hilbert. He was a formalist. So you see, even within mathematics, there are multiple schools. It's not like all the maths may seem simple and neat. No matter how simple and neat a system may look, it is still being studied by humans, and humans will have different ideas. So within mathematics also there are different schools: formalist school, intuitionist school, idealist school, right? So, or realist school. So so realist school, that is the simplest to understand. So they believe that numbers and mathematical entities, they are real entities, in the sense they exist independent of humanity or any thinker. So whether you and I are there or not, we can think, okay, this room will still exist, these chairs will still exist. It's not like they exist only as long as we exist. No, right? So similarly, realists believe that numbers exist as real. They don't exist in the material realm the way these chairs and tables do. They exist in some different realm, but they have independent existence. We only discover them. We didn't invent them. They are there already. We are just discovering them. So they will be there whether you and I are there or not. So numbers have an independent existence. Mathematical entities have an independent existence. So they take a realist stance. So realist school of mathematics takes such a stance. All right. There is another school called intuitionist school. They believe that numbers, mathematical entities, etc., they are nothing but products of our own intuition. They are constructed by us. And this they will extend by saying that anything which is not given a constructive proof cannot be said to be existing or cannot be said to be true. So they do not accept proofs like proof by contradiction. For instance, root 2 is irrational. We know. How is it proved? It is proved using proof by contradiction. You don't actually construct that root 2 is irrational, because there is no way you can do that. If you actually have to prove it by construction, you have to construct the infinite series of the decimal expansion of root 2. That is impossible. It's like you have to say this decimal expansion has an infinite series and no subsequence of this series is repeating. Again, if it is repeating, it becomes rational, right? But how to do that? It is infinite. You don't know. Just because some after 10 numbers it is not repeating, you cannot be sure that it may not be repeating after 100 numbers or after million numbers or after billion numbers. You don't know. Maybe a billion numbers themselves may be repeating, or a trillion numbers may be repeating. No matter how much you write, you are always unsure of it to be not repeating or repeating, right? So there is no way in which you can prove that root 2 is irrational by constructing the decimal expansion. So the method which people follow is proof by contradiction. Let's assume root 2 is rational. If it is rational, then it should be in the form of p by q, where p and q are, one can think this is in the most irreducible form, which means they don't have a common factor. And you square both the sides, you find p square equal to q square. This process is there, you learned in school textbook. Finally, we will arrive at a place where p and q both are even, which means they have 2 as a common factor, which means they did not, they were not in an irreducible form, which means our initial assumption was wrong, which means the original assumption that root 2 can be expressed in the form of p by q itself is wrong. So since root 2 is rational is wrong, the opposite is true. Root 2 is irrational. Okay. So we are proving that root 2 is irrational by contradicting the statement that root 2 is rational. Not by actually proving that root 2 is irrational. We are proving root 2 is irrational by disproving root 2 is rational. Okay. So this is proof by contradiction. They don't accept this kind of proof because they don't accept a particular, this proof is basically based upon a fundamental law of classical logic called the law of excluded middle. Classical logic has 3 laws: law of identity, law of non-contradiction, and law of excluded middle. Law of excluded middle says P cannot be both true and false at the same time. I mean, sorry, P cannot have any values other than true or false. Okay, there is no middle ground. Okay. Now, this may seem fine. Yeah, you have either true or false. That's how even reality works. But that's not how reality works. Particularly, you will understand this when you try to negate a negative statement. For instance, if I say, okay, don't talk in the class, don't talk during the class. When you negate this statement, does this mean you should talk after the class, or you can talk after the class, or you should talk before the class, you can talk before the class, or it doesn't matter whether you talk or not talk before the class or after the class? So many possibilities are there. Which of these possibility is the exact meaning of the negation of don't talk during the class? Right? So it is not like a simple one. Other example, if I say something is not black, it does not mean it is white. It can be million other shades, million other colors, right? So there are not just two colors in this world. Similarly, there are not just two truth values in this world. It can be something can be partially true, half truths are there. So one can think of these kind of things. Like I said, model logic tries to deal with something like this. Something is necessarily true, something is possibly true, something is necessarily false, something is possibly false. So you can have different modalities of truth, different ranges of truth. So there can be an entire spectrum of truth values, completely true, completely false, and there can be something in between. All right. So this law of excluded middle does not neatly sit on with reality. Okay. So the intuition is they first of all reject this law of excluded middle. They say no. If something is not true, it means it is not true. It does not mean it is false. If something is not black, it means it is not black. It does not mean it is white. Okay. No, I don't know. If root 2 is rational is false, it is false. That does not mean root 2 is irrational is true. That proof has to be built on its own. That proof has to be different than this proof. Okay. But that proof involves infinity, actual infinity. So if you don't want to use proof by contradiction, what kind of proof can you use? They want to use proof by construction. For normal finite proofs or finite numbers, when you're dealing with, proof by construction can work. Okay. But when you're dealing with infinities, proof by construction cannot work because you can never construct infinite numbers. You can never write infinite steps. For instance, if you have to construct a simple infinite number, how do you construct? You take a finite number, you keep adding one, no matter how many times you keep adding, you can do only finite steps, no matter how big that those finite steps are. And you can build only a finite number, no matter how big that finite number is. Instead of one, you can add million, you can add billion, you can add trillion. No matter how big finite number you add, you can add it only finite times. And no matter how big the number of finite times you do, it is still a finite number. You cannot jump from a finite number to infinity just by taking bigger finite steps. No, you have to take an infinite jump to reach infinity. That's the only way. But that is not possible. So you can never prove any theorem or any statement about infinities using finite steps. So you can never prove anything related to infinities using proofs by construction. So as a byproduct, they do not accept actual infinities. We will discuss a bit about actual infinity and potential infinity later in the course, in a couple of classes. But the idea is infinities, actual infinities don't exist. You cannot prove, you cannot construct any proof related to them. So they don't exist. Okay. Another byproduct of this is they don't accept real number line continuum being made up of, first of all, they don't accept that. And second thing, they don't accept that it's being made up of infinite points because it's infinity. The moment you bring in infinity, you have many paradoxes. For instance, something very simple. Suppose you just take a finite line segment. All right. If I cut or I split that line segment at its midpoint, what will happen to this midpoint? there are four possibilities. Either it will go to the left half, or it will go to the right half, or this point itself will be divided into two, or this point completely falls out and subtracted from the original line segment. Okay. Now, whichever of these four possibilities you take, you will run into contradictions. Why should it go to left half instead of right half, or right half instead of left half? It is not logical. So those two possibilities are gone. If it is divisible into two, that is violating the definition of point itself, because point is indivisible. That is also gone. If it is being subtracted, if it is being treated differently from the left half and right half, then now you continue this process of splitting the new line segments which you are getting. Now I split my left line segment, the right half, right line segment, left half, right half. I get now four new smaller line segments. I split them further. Again, I get new smaller line segments. At each step, I'm subtracting the midpoint. Okay. Now, you notice one thing. We know that the length of the original line segment is equal to the sum of the lengths of the smaller line segments, no matter how many times we divide them. But if you follow this process where you are subtracting the midpoint and you are ignoring it from the equation, okay, at the end, when you are continuing this process infinitely, you are getting smaller line segments, you are again splitting them, again splitting them, again splitting them. Finally, you are subtracting all the midpoints and you are ignoring them. Finally, you are left with only two endpoints. But the sum of these two endpoints should be equal to the original line segment's length. That is not possible. So even this case is not working. Even this scenario has a problem. Can you think of a fifth scenario? No, I don't think so. So all this, none of these scenarios are working because you are dealing with infinities. You are dealing with infinite points. Infinite number of single points. Okay, fine. Yeah. So you'll get infinite number of single points of each small line segment endpoints. You will get infinite number of single points. Fine. Now, even then, the sum of these infinite single points will be zero. Lengths of the smaller line segments, sum of those lengths should be equal to the original line segment length. But you are getting points at the end. Each point is of length 0. Even if you add them up, you will not get the original line segment length. So that is again a mystery. Simple thing is, how do I construct a line or a line segment using points? You see, to construct anything, you have to arrange some things. You have to arrange the parts. If you want to construct a house or a wall, you have to arrange the bricks in some way. If I have to construct a real line segment, I have to arrange the Euclidean points in some way, which means I need to place the points next to each other, which means the points should have neighbors. But in principle, there cannot be a neighboring point, because between every 2 points, there are infinite points. The moment you look up within these infinite points, you take any 2 points, again, between those two, there are infinite points. So you can never find a neighboring point between for any given point. So you can never place any point next to other point. Then how can you construct a line? So you cannot construct a line. So a real line is only imaginary. So since there cannot be a proof by construction for a real line, it is not accepted by intuitionists. All right. So anyway, this is one school. That is one school, and then formalists is one school. They believe that numbers, entities, sets, this, that, it doesn't matter whether they already exist and we discovered them or we invented them. None of those things matter. The thing is, there are some entities which we are dealing with, and we are using some symbols for them, and we can manipulate these symbols according to some rules. So there are some formal rules which these entities follow, whether they pre-exist or whether they are given to me or whether I invented them. Whatever is the case, they follow some rules, and there is some neatness to the system. So this is all I take. I define these rules and I play with these rules, and I work with this system. Okay, so my system is formal, it is neat. This is all I'm concerned about. So Hilbert was one such mathematician. He was one of the greatest mathematicians. He's considered to be one of the greatest mathematicians of all time. So he gave a set of 23 problems for the 20th century in the year 1900. So these are very tough problems, and he said it might take at least a century to solve them, right? Most of these problems are solved, but some are still unsolved. Okay, but the basic idea is using these problems. You see, he was a staunch believer that maths is neat. Maths is so neat that it can prove itself. Whatever statements are there in maths, they can be proved within mathematics. It is self-explanatory, it is self-complete, it is self-sufficient, and it is neat. There is a gut belief. Even if someone asks you if maths is like this, intuition, by intuition you may say yes, maths may be like this. Right now I may not be able to prove that, but maths seem neat, maths seem very powerful, consistent, and so on. So Hilbert also believed that, and most of these problems they wanted to establish. He wanted to prove that mathematics is complete, consistent, and decidable. He somehow believed math has all these features. So he, as part of his 23 problems, he gave this task. In case any of you can prove this, that math is complete, consistent, and decidable, it will be great. Okay. Now, it is sort of shown that maths is none of this. It cannot be complete and consistent or decidable. So the first two parts, that it can neither be complete nor consistent at the same time. If it is complete, it cannot be consistent. If it is consistent, it cannot be complete. So both are related. Okay. So it was sort of proved by someone called Kurt Gödel. I don't know how many of you heard of Gödel's incompleteness theorems. So what does this theorem say? Any system capable of doing basic arithmetic cannot be both complete and consistent at the same time. You see, in logics, there are different levels of logics. Even in classical logic, there is first order logic, second order logic, third order logic, and you can go on to higher order logics. Now, to capture mathematics, at least to perform arithmetic operations, you need a logic which is at least as complex as second order logic. Okay. So, mathematics is at least as complex as second order logic. So Gödel sort of proved that any system which is at least this complex, okay, it cannot be both complete and consistent at the same time. So how did he do that? His proof is slightly complex, but I'll give you a very simplistic idea of his proof. Now let's imagine there are some 4 statements. Some simple statements like 2 plus 3 equal to 5, area of circle is pi r squared. We can also have false statements, right? Area of circle is some other formula, 2e plus pi, something like that. And then S4 statement is that S4 is not provable. Okay. Now among these, some statements can be true, some statements can be false. These two are true. This is false. Okay. Now, what about this statement? Is it true or false? That's a different thing. Again, among these, some statements may be derivable, some statements may not be derivable. Okay. Now, assume all the true statements here are derivable. Okay. So S1, S2 are derivable. Suppose S4 is also derivable. If S4 is derivable, what does it imply? You are deriving that S4 is not provable. So you are deriving a statement S4 is not provable, but you are proving the statement that S4 is not provable. Okay, which means you are proving both S4 and not S4. Fine. See, 2 plus 3 equal to 5, you are deriving through some steps. That is a conclusion of some premises. Again, area of circle is pi r square. That is a conclusion of some previous premises. Now, S4 is not provable is a conclusion of some of the previous premises. Okay. So this so-called S4 is not provable statement is actually being proved because it's a conclusion. So you are proving S4, but when you say you are proving S4, you are proving that S4 is not provable also. So you are proving both S4 and not S4. Okay, which means your system is deriving all true statements S1, S2 and S4, but it is inconsistent because it is deriving both S4 and not S4. It is complete because all true statements are being derived, but it is inconsistent because it is deriving contradictory statements. Okay, so if it is complete, it cannot be consistent. Fine. So you have it out. So if all the true statements are derivable, then the system is complete. But inconsistent since the proof of S4 implies not S4 as well. Okay. So if you are proving S4, you are indirectly proving not S4. You cannot prove one without the other. You cannot prove only S4 and not S4. That's not possible. Fine. So if it is complete, it has to be inconsistent. All right. Now let's assume that S4 is not provable or not derivable. All right. Which means S4 is true. S4 says it is not derivable. It is not derivable. Fine. Which means there is at least one true statement in your system which you actually cannot derive. It is true, it is not derivable, that is a statement, and it is actually not derivable, which is perfectly fine. It makes S4 true because it's actually not derivable. But it also means some true statement is left out. You are unable to derive it. So your system is consistent, there are no contradictory statements, but it is incomplete. Okay? S4 is not being derived, it is true, which means you are missing out a true statement, which means your system is incomplete. It is not inconsistent because you are not deriving contradictory statements. Fine. On the other hand, if S4 is not provable, then it means that there is at least one true statement which is not provable or derivable and hence the system is incomplete, although consistent. It is consistent because you don't have contradictory statements, but it is incomplete because some true statements are left out. At least one true statement is left out. Okay, so this is a simplified version of Gödel's proof. His proof involves a lot of mathematics. So now this thing is gone. If math is complete, it cannot be consistent. If it is consistent, it cannot be complete. Okay, so at least these two cannot be true together. Fine. Now the third thing, that is decidability. So this was disproved. Again, this is also not true. Maths is not decidable. Who proved it? Turing. So Turing, in the process of proving that maths is not decidable or disproving the decidability of mathematics, he came up with the idea of Turing machine. Okay, so Turing machine is a byproduct of this exercise. Okay, so in the process of, so he did not set out to disprove decidability, he set out to prove, but he ended up disproving it. Okay, so in the process of proving or disproving, decidability of mathematics, Turing came up with the idea of what today we know as algorithm. And a device called Turing machine which can implement any algorithm. So what Turing understood is that, you see, there is no simple way to say when a system, when a statement is given, whether the statement is derivable from a system or not. There is no simple way. You have to come up with a generic method, some step-by-step procedure, using which takes this statement as input and also the axiom set as input and tells whether this statement is derivable from this axiom set or not. Okay, so this step-by-step procedure, to run this step-by-step procedure, you need some idea of a machine. Okay, so he invented the idea of a machine which follows the step-by-step procedures, and he called it Turing machine. It is a mathematical model of a machine which takes instructions and executes them step by step. That's all. When you look at the machine's model, it looks very simplistic, but it will be really amazing to think that such a simplistic machine is so powerful. Whatever we can do on, whatever complex things we can do on our computers, all these complex things can be done on that simplistic machine. It's quite simple. It's just a tape with some symbols. It has cells, and each cell has a symbol, and you can override this symbol and go left or right. That's it. You can move this tape left or right. There will be a head which points to a cell. This cell has a symbol, and that symbol you can change. Then move on to right or left and rewrite the symbol in that corresponding cell. That's it. This is the process. You can repeat this process as long as you want. This is all that Turing machine is. That simple model of Turing machine is so powerful that it can do everything which our computers can do. Just imagine. So, but anyway, so Turing came up with this idea of Turing machine, and this was the first. Uh, this was a proper formulation, an idea of algorithm or an idea of a machine. Until then, people were sort of using calculators or even sort of some kind of computers were also there. But it is after Turing gave this definition of a computer or a Turing machine, the real ability or the limitations of a computer came to be known. The foundations of computer science were laid with this work. Okay, and whatever other models of computation which we see, like we will look at regular languages, context-free languages, context-sensitive languages, and finally Turing grammars. But first Turing machine came. That was invented by Turing. Later, these different levels, these are sub-levels. Among all these four levels, Turing machine is the most complex one. But the sub-levels were sort of discovered later by Chomsky. That we will see later. But the idea is the motivation behind this course and the motivation behind Turing machine is the attempt to prove the neatness of mathematics. They were mathematicians, and in the process of trying to prove the neatness of mathematics, as a byproduct, Turing came up with the idea of Turing machine. Okay, so now what is the relation between this decidability of mathematics and Turing machine? So that's what I'm coming to. Turing basically translated the problem of decidability of mathematics into something called halting problem in computer science. So what is halting problem in computer science? Does anyone know? Okay, so imagine you say we write many programs. Now, usually a program takes an input and gives an output, or it may not give an output, it may just end without giving an output. Fine. Now, one can think of any kind, different kinds of programs. Say, suppose I can write a program which takes a number and prints it square. I can think of a program which takes a number and prints that number minus one. Or I can write a program which takes two numbers and prints their sum or prints their product or their division, whatever it is. Now, and there can be programs with loops, without loops, or I can write a program which does not print anything. It just ends, it just stops. Anything is fine. Now, sometimes it may happen that I may have a loop in my program and my program may never halt. It can be due to different reasons. One is there can be an error in my code, or error not exactly as an error that the computer finds it. It's a human error in the sense, suppose I am subtracting a number and I want to stop the code when it reaches 0. Okay. Now I forget putting the terminating condition. I just keep subtracting, but I forgot keeping the termination condition. So the code will run forever. It will keep subtracting minus one, minus one, minus one. It will keep doing that and it will go on infinitely because it will never reach the terminating condition. That can be one way. Another example can be, my code is perfectly fine. I have put the terminating condition also, but I did not imagine an input which may take this code into infinite loop. For instance, suppose I want to know what is the quotient when a number is divisible, when a number is divided by 2. Okay. One way is you actually use the division operation. Another way is you write a loop saying for n, while n not equal to 0, reduce n, do n equal to n minus 2. Okay. Now the number of times this loop runs, that is the number of times that number is divisible by 2. That's all, right? If it runs 4 times, that number is 2 into 4. If it runs 10 times, that number is 2 into 10. Now, this seems fine, but the problem comes when you give an odd number. You see, somehow in my mind, I was thinking only of even numbers and I wrote the code keeping only even numbers in mind. What did I say? if until n is not equal to 0, you run the loop. So I'm assuming n will touch 0 at some time. But what if n skips 0 without touching it? If it is an odd number, it will be like 5, 3, 1, and then -1, -3, -5. It will not touch 0. So this condition is never satisfied. It will never become 0. So it will go in an infinite loop, right? So here it went into an infinite loop, not because there is a problem in my incompleteness or my code is incomplete, but the input set that I thought of, that is incomplete. So there are gaps in my thinking of the inputs, and some user utilized exactly this gap and gave the input. That is how even hacking is done. In hacking, it's not necessary that your code itself has a bug. Bug can be of various types. That is, you forgot putting the terminating condition. That can be one kind of bug. Another kind of bug is you have put terminating condition, you have written everything, but you did not think of some special kind of input which may break your code. So that is what hackers exploit. So they find the cracks in your code. For instance, see something as simple as say division program. I take two numbers, A and B. I do A by B and I print the output. Simple. I write the code and I print it. But out of a million cases, I should also imagine the worst case, that what if B is 0? Someone exploits this and they give B as 0 and they break your code. Division by 0 is not defined even in computer. It will break. Your code will exit with an error. Not syntactic error, but runtime error. When you try to run it, then it will give an error. Okay? So even you will not know that, because it is a runtime error and it is purely dependent on the input which the user is giving. When you run it, normally when you compile it, it will not give any error. It compiles neatly because it's A by B, syntax is all fine. It is taking, even when you give many inputs and you run it, even then it runs neatly. But some special input which you did not think, the hacker thought, and he gave 0 and he broke your code. Okay, so you should think of every possible input which may work, which may not work. When you are writing, critical codes which are deployed for very sensitive scenarios. Okay, so this can be one case. So you don't know when your program may run, when your program may exit with an error, or you may not know when your program may halt, when your program may get into an infinite loop. Okay, so can we come up with a meta program which takes a program and an input and tells me whether this program halts on this input or not, so that I need not waste my resources in actually giving this input and running on this program. If I know this program will not halt on this input, then I will not run this program on this input. So first I will use the meta program to tell me whether this program halts at all on this input or not. If it says it will halt, then I'll run this program on this input. If it says it will not halt, then I'll not run this program, right? But Turing proved that such a meta program is not possible. Such a meta algorithm is not possible. Our individual programs are algorithms in themselves, and each algorithm can take different inputs and give different outputs. Now I want to come up with a meta algorithm which takes individual algorithms and some inputs and tells me whether each of these algorithms or this particular algorithm halts on this particular input or not. Turing said it is impossible. He deployed a method similar to Gödel. Again, he uses some counterintuitive or self-contradictory kind of a scenario. We will look at that later when we deal with Turing machines in the later half of the course. We will look at the proof as well. But a naive way of understanding, not exactly the proof, but a naive way of understanding is, suppose your program is running, it is not halting. Now, there is no way for you to distinguish, for you to know whether the program is not halting because it just needs more time or because it is running in an infinite loop. You don't know, because some programs may take months or years to halt. You may think, okay, it is going on forever, so there is an error. But maybe if you wait a year, it may stop. Or you may think, okay, if I wait a year, it may stop. It may not stop. If you wait 2 years also, it may not stop. If you wait 10 years also, it may not stop. It may never stop because it's going in an infinite loop. So these two scenarios you cannot distinguish. So this meta program also cannot distinguish when the program is not halting. It does not know whether it is not halting because it just needs more time or because it is genuinely stuck in an infinite loop. So that is not possible. So Turing showed that. So by proving that halting problem is undecidable, he sort of showed that mathematics is also undecidable because you cannot come up with a generic meta algorithm which, given a particular axiom set and a particular statement, can tell you whether this statement is derivable from this axiom set or not. He said it is not possible. You have to manually verify. You cannot automate it. That's all. Okay. So this is the thing. So now maths, you see, it is not complete, not consistent, not decidable, but still it is neat. This is maths. We sort of deal with such open foundations, but we find things neat because somehow the building is standing fine. The foundations are open, the foundations are loose, but the building is standing fine. We don't know why or how, but it's working. So let it go. This is how we act in life also. You see, if you want to go to your own existential foundations, one can ask million questions. Okay, like when did the universe begin? When did the existence or the life on earth begin, or the life in this cosmos begin? And how did life be born from non-life? Was there life since the beginning, or beginningless time? Or if it began at some point of time, how did it begin? There was matter. From matter, how is life born? So all kinds of open questions one can ask, but we don't ask. Our life is still fine. No, even without asking these questions, even without addressing these questions, our life is going on fine. If you in fact open up this Pandora's box, you will go mad, right? Life will become chaotic. But there are people who have this sort of itching, one says, no, they want to open up these things and they want to ask these questions. So this exercise did not lead to the proof that maths is decidable, but at least it led to the byproduct of something called Turing machine. It gave rise to computer science, which is a great byproduct, right? So you may not exactly find what you're looking for, but you may find something useful. Okay. In fact, there is a paradox called Meno's paradox, which says to know anything, you should know everything. So either you know nothing or you know everything. You can't know anything in between. For instance, the idea is, suppose you you go out looking for something, to know something or in search of something. Now there are two possibilities. Suppose if you don't know what you're looking for, your search will never end because you don't know what you're looking for. If you already know what you're looking for, then there is no need to look for it. So in either case, you need not venture out to look for it. So either you know it or you don't know it. That's it. You can't know anything new. So it means, so the explanation for this, this is, we know everything already, but still it seems we know something new, not because actually something new is added to our knowledge base. It is just that whatever is already there, some layers are uncovered within our knowledge base. That's all. We already know those things. It is just that we don't know that we know. That's all. So it's just being uncovered. Okay. So this is Meno's paradox. Either you know everything or you know nothing. There can't be anything in between. Okay. So just one more minute. All right. So, like Turing machine, there was Turing's teacher, Alonzo Church. So he came up with something called lambda calculus. Actually, both these were invented independently at the same time, in the same year. Lambda calculus was invented by Alonzo Church and Turing machine was invented by Turing. And later they found that both are equally powerful. That Turing machine is as powerful as lambda calculus. So whatever can be done on a Turing machine can be done using lambda calculus also. You can also find it in as a function in programming languages. In Python or something like that, you can search lambda programming or lambda calculus programming. You can write a function like that. Later, people found that this is also equivalent or as powerful as cellular automaton. Cellular automaton, for you to understand this, you can check up something called Conway's Game of Life. So this is again very simplistic thing, but very powerful. You just have a grid of cells in which some cells are black, some cells are white. Now there are some rules. Depending on which cells are black, which cells are white, the neighboring cells can change their color, black to white, white to black. And this can give entire reality or entire cosmos. You can even build a Turing machine in cellular automaton. A Turing machine can build itself. It's like a 3D printer can print itself. Similarly, a Turing machine can build itself. Okay, so all these things are there. All right. So later, now we will get into in the next class, we'll get into the mathematical foundations of automatic theory. We'll revise some mathematical concepts like set theory, etc. But before that, let me take the attendance.